Welcome to Lecture 1 of Introduction to Quantum Computing Systems. In the previous lecture 0, we have learned about the high-level state of the play for quantum computing system research. From now on in this course, we're going to learn more systematically what quantum computing is and how quantum computing system research look like. And we're going to do that with 3 modules. The first one is Introduction to Quantum Computing and Programming. In this module, we will be talking about the fundamentals of quantum computation and really what is the quantum computational thinking. And the second module, we will be talking about components and principles of quantum computer architecture. And moving on to the third module, we'll be working with more realistic quantum computer systems, namely noisy systems, and talking about optimizations in the presence of noise. So in this first lecture, we will be answering really 3 key questions. What does quantum computer do? There are certain types of problems that quantum computers are particularly good at solving, and we want to identify and understand what they are. And the second question we want to ask is why quantum computing? Why is quantum computer faster than classical computer? Why do we build one? And lastly, how do we build a quantum computer? Both from the conceptual, theoretical level, as well as the realistic, physical or architectural level. Okay, so let's move on to this first question. What problems are quantum computer good at solving? In the 1980s, physicists have started thinking about how do we learn about quantum mechanics better. Quantum mechanics are really difficult to simulate with classical computer. Physicists like Yuri Menon and Richard Feynman proposed this idea of using quantum computer, a type of computer that utilize quantum mechanics, to simulate quantum mechanics itself. The intuition is that to simulate quantum mechanics, for example, the electronic structure of a molecule, suppose we have a molecule of n electrons, then with a classical computer, it is believed that we need exponential number of sort of computational steps or amount of resource to simulate all the interactions between the electrons. Whereas quantum mechanically or with a quantum computer, it is believed that we can do that a lot faster. But it is challenging to do that because we need to build a computer out of quantum mechanics itself to start with. And then in the 80s and 90s, a group of computer scientists have been thinking about a question: is quantum computer good for solving classical computational problems? And computer scientists like Deutsch, Josa, Bernstein, Vasirani, and Simon came up with particular computational problems or mathematical functions that quantum computer are very good at solving, better than its classical counterpart. What sparked the excitement from general public is when 2 discoveries of daily computational tasks can be solved with quantum computer very efficiently as well. Namely, Peter Shor came up with a quantum algorithm for factoring large numbers into prime factors, and as well as solving the discrete logarithmic problems for cryptography. And a year later, Love Grover found an algorithm that performs database searching better using a quantum computer. So the discovery of these algorithms really made people started thinking about what kind of daily computational problems that quantum computer are good at solving. later on, these algorithms are generalized to solve many other tasks. And here's just a list of some of the examples of those algorithms developed in recent years. And in fact, we can categorize sort of classes of applications that quantum computers are very good at solving. And quantum chemistry, for example, was generalized from the quantum simulation idea. Security applications were generalized from Shor's factoring algorithm, as well as Grover's search algorithm. And they also inspired a series of applications in optimizations, combinatorial optimizations, etc. And recently, people have been starting thinking about its application in machine learning because of the new discovery of parameterized quantum algorithm, or in other words, hybrid quantum classical algorithms. So we'll be getting into those algorithms in the future for this course. But for now, this is just an overview of how the development of quantum algorithms have been for the last decades or two. So next, I want to move on to the discussion of how do we really utilize quantum mechanics for computation? Well, to answer that question, we need to understand what is computation. Speaking from experience of building classical computer, what we have done successfully is to abstract some physical substrate to a notion of bits. And they can be implemented physically or realized by a bunch of things like transistors, vacuum tubes, voltage in wires, even abacus. They all come to be abstracted as bits, 0 or 1. And this is how our digital computer store information, compute information, and so on. This can be generalized to build a quantum computer. So all we need to do is to find quantum mechanical properties and abstracted them into a notion of quantum bits or qubits. Here are some examples of things that we believe are potential implementation of qubits. Some of them uses atomic structures, atoms or ions or photons. Others are artificial atoms and, for example, superconducting circuits. So now here comes the question of what's the difference between a bit and a qubit, and why is a qubit better in solving certain computational tasks? The first few properties of from quantum mechanics that I want to talk about is superposition and interference. The way that we are going to introduce in this course is through sort of the eyes of computer scientists. What are the information or computational aspects of these properties? To understand that, I want to compare what a bit and a qubit is with the following exercise. I want to list the possible states in a bit or several bits, and then compare that with possible states in qubit and number of qubits. Okay, for a single bit, we know it can be in a state of 0 or 1. And for 2 bits, then it's just 0, 0, 0, 1, 1, 0, and 1, 1. Similarly, we can generalize that to n bits from 0, all 0 to all ones. So here we have n bits, and you will get 2 to the n number of pos states, so one of the possible states. Okay, so let's now take a look at what is a qubit. Now for qubits, we will need this notion of superposition. So a qubit can be in the state 0 and 1 at the same time. we write them as a linear combination with coefficients alpha and beta respectively. And if you measure this qubit, you will have some probability observing 0, some other probability of observing 1, and these probability will be related to these coefficients alpha and beta. What I want to show here is how quickly this qubit state space grow as the number of qubits increases. So for 2 qubits, we will need a linear combination of all 4 possibilities. Alpha 0, 0, 0, and then for 1, 1, and then 1, 0, finally 1, 1. 2 qubits can be in these 4 possible states at the same time. For total of n qubits, we will need 2 to the n number of terms. So this superposition over exponential number of possible states is essential in understanding the power of quantum computation. Well, computation is just a transition of states. Start with state 1, state 2, and then state 3, and so on. So let's compare the possible transitions for bits versus for qubits. We're going to look at 3 types of transitions. The first one is deterministic transitions, second one, random transitions, and finally, quantum transitions on qubits. For deterministic transitions, where you start with 0, 0, flip the second bit and will become 0, 1, and then maybe later on it becomes 1, 1, and so on. Transitions in this context is just functions that maps the input bits to some output bits, okay? What if we add randomness into this process? So we start again with 0, 0. A random transition will look like we flip the second bit with some probability. So if we write the probability of each transition on the edge, then we will see we flip the second bit with probability 50%. And now we can keep doing this random transitions, maybe this time with a different probability weight. With some probability, you will not flip the first bit. And with other probability, you will. Similarly, we can do the same thing for the second case, 0, 0, 1, 0. So at the end, you will end up being in the final state, 0, 1. And this probability can be calculated by multiplying the probability along this path from the start state to the end state. And we can write them down here. So with 10% probability, you'll get 0, 1. And here, 40% for 1, 1. Another 10% for 0, 0. And then finally 40% for 1, 0. Okay. For quantum transitions, something very similar happens. But this time, let's say this is a quantum bit. Again, we can transform 0, 0 into different possible states. In this case, let's say it's 0, 0 and 0, 1. And then we can keep branching out as we did before. Suppose we have 0, 0 here, 0, 1 here, 0, 0, 0, 1. But this time for a quantum transition, the weights, in fact, can have negative coefficients or even complex numbers. For the first example, first transition, let's just use 1 over square root of 2. But in the second case, we allow negative 1 over root 2 in one of the transition. As a result, we can calculate the final weight for each possible output state, again, by multiplying the numbers along each path. So over here, this is 1/2. another 1/2, 1/2. But the last one is negative 1/2. So what is the final state? The final state after this, we will end up in a linear combination of all the possible outcomes over here. So with the appropriate coefficients, 1/2 of 0, 0, 1/2 of 0, 1, and 0, 0, minus 0, 1. As you can see, now we have 0, 1 canceling each other because of the negative sign. 0, 0 add up to 1 times 0, 0. This is what we call interference, because as you can see, some of the state interfered destructively and they cancel out. Other states interfered constructively, so they add up. Now, if we think about these type of transitions more carefully, it allows us to do computation differently. Suppose you have some right answer that is 0, 0, and some other wrong answers that is 0, 1. What you can do to maximize the success probability at the end is by creating interference and canceling out those wrong answers and leave only the right answers in your output. This type of interference is only possible if you can have negative coefficients in these transitions. And that is precisely what quantum transitions allowed us to do. Random transitions are in fact stochastic processes, and quantum transitions are what they call the unitary processes. And we can use more rigorous mathematical representations for these transitions by writing the possible states as vectors, and then possible transitions as matrices. Next, we are going to talk about another interesting properties allowed by quantum mechanics in the context of computation. This is called entanglement. To understand entanglement, we're going to compare two different quantum states, one that's entangled and the other that's not. And then we're going to see what is the consequence of the measurement outcome due to entanglement. So let's take a look at two different quantum states. And the only difference between the two states are in the coefficients. So the first one, the sign 1/√2 for 0, 0, 1/√2 for 1, 1, and 0 for the rest. And for the second qubit, we'll assign 1/2 everywhere. Now, assuming these two states are all valid quantum states, let's take a look at the difference between the two by rewriting the second one. Notice that we can, in fact, factor out the first qubit out of the quantum state. First, the coefficients, and then grouping the first two, we have 0 for the first qubit and 0 plus 1 for the second. Grouping the third and the fourth, we get 1 times 0 plus 1. Now we can group it even further. So what we get, in fact, is 0, 1, 0 plus 1 for the first qubit. Same thing for the second. Let's distribute the coefficients as well. We will then end up in a product of this form. It is a product of two qubits. Can we do the same thing for our qubit on the left-hand side? Well, the answer is no. So in other words, there's no way to write the qubit here in this form for any possible alphas and betas. Okay, so now let's take a look at the measurement outcome for the two qubits. Let's get back to the unentangled qubits on the right-hand side. If we can write them as a product, then measurement becomes independent. So the consequence is that we have independent measurement outcomes. For the two qubits. Whereas here, you will end up with some correlated measurement outcome. And this correlation in this example is that the two qubits will always have the same measurement outcome. We're going to revisit this concept of entanglement in a future lecture because this entanglement property also plays a crucial role in the power of quantum computation. So next, we're going to talk about the different models of computation, or in other words, how do we build a computer out of those bits or qubits? Well, classically, we have several conceptual models of computation. For example, we have Turing machines, finite automata, lambda calculus, or circuit models. To some extent, they are equivalent. One can be used to simulate another, but some might be considered relatively easier to generalize to a quantum model. In particular, the model we picked today is the circuit model. So what is the circuit model for computation? If you have an electrical engineering background, then you're already familiar with the circuit model. This, for example, is a AND gate, takes in two inputs, two input bits, x1 and x2, and output x1 and x2. In general, for the circuit model, you will have several input bits. You pass it through some circuit for computation, and you end up with some output bits. We can easily generalize this model for quantum computation by passing in input qubits through quantum circuits, which consists of quantum gates, and you'll end up with output qubits. Now, one of the advantages is that you can pass superposition states through the quantum circuit. We will be using this quantum circuit model extensively in the rest of the course in order to understand how quantum algorithms work and how information is processed. But we also need an architectural model that's closest to the implementation of a quantum computer. So here is how a quantum architecture look like today. We have something called QPU that houses array of qubits. And it's controlled by a host CPU where the description of a quantum circuit is stored, and it performs the generation and optimization of control signals. Data also feed back to my host CPU. After we have completed quantum computation, we can read out the measurement outcome from the qubits. Now, this is an architectural model that is relatively easy to reason about because everything to the left of this interface is classical and everything to the right is quantum. Now, what is this course about? This course is about quantum computing system design, which is a study of the functionalities and optimizations at the classical quantum interface. So for the rest of the course, we're going to carefully define what the classical quantum interface is and discuss research opportunities and challenges that we still face today.